Here's a few examples of what we were just talking about, looking at expressions and trying to decompose them and break them apart. So in this section, yeah, we're focusing on finding a GCF. So I don't want you to ever lose this focus. This is the first section of Chapter 6 for a reason, because every problem that we look at from here on out, you want to approach with the idea in mind. What do these terms have in common? Can I find something in common? The answer to that question is not always yes. But you always want to have the first thought. What do they have in common? Do I see anything they have in common? And hopefully that's pretty apparent. And if I'm looking at number 1, right, a pretty tame expression, right, but hopefully you look at this and say 4 and 12, yeah, they have something in common. What are they both divisible by? So we want to find out what that GCF is, right, in every case. So between 4y and 12, the only thing that these guys share is a number, right, because this one doesn't have any y's in it. So, right, their GCF, right, is going to be 4. 4 divides into 4 and into 12. So we can remove a 4, and once we find the GCF, we open up one set of parentheses and say, well, what would be left over if we divided by 4? Right, well, 4 divided by 4 is 1, and we still have a y. So I guess we don't need the 1 in there anymore. And 12 divided by 4 is 3. And there we have it. 4 equals y plus 3. And these are super easy to check to see if you've done them correctly, because you can just say, I'm going to distribute this 4 back in here, and hopefully you get back to where you started. Yeah, 4 times y is 4y. 4 times 3 is 12. Now you know you did it correctly. All right, on to this next term. All right, let's identify what the GCF is. A little more complex here, but we can still find it. Between 6 and 8. The largest number that divides into those, 2. And between x squared and x, remember with variables we look for the lowest power we see, that would just be x. So we can remove a 2 and an x from each one of these terms. So once we say we can do it, now the task is let's do it. So I'm going to divide 6x squared divided by 2x. That's one way to think about it. I don't really like to think of division. That's kind of a negative operation in my head. I'd rather try to build things. Building things and constructing them seems easier to me. So I like to fill in the blank and say 2x times what? What would I need to build 6x squared? Okay, 2 times 3. All right, will give me 6. I have 1x here. I would need one more x and x, to multiply to get x squared. So I like the building idea instead of the deconstructing idea. I go to my next term and I say 2 times 4 would give me 8. Right, and I have an x already in this, so 2x times 4 would be 8x. I don't need any more x's here. It's a really common mistake to think that you need an extra x here, but if you did that, 2x times 4x would actually be 8x squared, and I don't want that many x's in this problem back there. I just want 1x, and I already have it. So there is our answer. 3, I've got more terms, but that doesn't make it any more difficult. I just have to evaluate all of them and say, all right, well, what's the common factor between 7, 21, and 14? GCF. Well, numerically, hopefully you came up with 7. 7 divides evenly into all these. All right, in terms of a's, are there some a's I can take out of every pile? Yeah, the lowest exponent is 1, so 7a I can remove by every term, from every term. All right, so now let's try to build up to this expression up here. 7 times what? 7a times what would give me 14a to the third. So 7 times 2. All right, I have one single a. I need to get to 3 a's, so I need to bring along 2 more to the party. All right, go to the next term. 7 times 3 is 21. All right, I have one a that I'm bringing along. I want to end up with a total of 2 in this case, so I need to bring one more a. Sometimes people will stop here and think that they're done because they're saying, I'm removing a 7a from the expression, and I have a 7a here, so I'm taking the whole thing out. Right, if you do that, you're not going to be right, you're going to be off. Because if I wanted to distribute this back in here, yeah, 7a times 2a squared is 14a to the third. 7a times 3a is 21a squared. Right, but how is this term going to show up if I don't have something here to make it show up? So if I have 3 terms to start off, I'm definitely going to have 3 terms in my set of parentheses. We still need to figure out 7a times what will give me negative 7a. So that negative is going to stay, and 7 times 1 will be 7. Right, and I have 1a, and I only want to end up with 1a, so I don't need any more a's in this back term. But hopefully this does show it. If I distribute it, 7a times 1 is 7a. So that's perfect. That's exactly what we want. Right, so if you ever factor out the whole term, you're always going to be left over with a 1. A little more complex over here at 4. Let me change it a little bit. Let me put a y here. Let's identify what that GCF is. Between 12, 16, and 8, numerically speaking, I think they're all divisible by 4, and that's the most that we can divide them by. For the x's, the smallest power of x is just x. For the y's, the smallest power of y is just y. We're removing that from each pile. Or if you want to think about it in a more constructive manner, you can say, well, I'm trying to build this expression. 4xy times what would get me back up here? All right, so 4 times 3. I have 1x that I'm bringing. I need to bring one more x. X times x would be x squared. All right, there's 1i being brought to this party. We need to bring 2 more y's, y and y squared, to get y to the third. That's our first term. Okay, next, 4 times 4. 16. And I have 1x. I need to bring one more x along, x and x, to get x squared. In terms of y, I already have 1y. And I only want 1y, so I don't need to bring any more along in this term. All right, next piece. 4 times 2 is 8. And for x and y, I only have 1 here, and I only want 1 here. So I don't need to bring any more x's or y's along to this term. And we would be done. Number 5 is a little weird, and it probably looks strange compared to our other expressions that we were dealing with, but it does relate to section 6.2. This single term and this single term, they do have something in common, but what they have in common is actually a binomial in common. They both share an x plus 1, right, which is a little strange. You might be inclined to think, well, I can distribute this out, and I can distribute this out, and see what everything has in common. You could do that, but you would run into a little wall where you end up seeing that they don't have anything in common if you do the distribution. So this is actually a nice way to see this problem, because we can see that this first big term has an x plus 1 in it, and this other term has an x plus 1 in it. So they are sharing that x plus 1. Right, the same way that these terms up here, were sharing an x and a y. Right, so they have a GCF of x plus 1. You can have a greatest common factor that's a whole expression. Every term in this expression has this expression in it. So my GCF is x plus 1. I'm going to open up a set of parentheses and say, what would be left over if I looked at this whole expression and said, what would happen if I took an x plus 1 out of it? Or in other words, if I have an x plus 1, what do I have to multiply it by to get back up to this whole term? Well, I would need a 3a. 3a times x plus 1 gets me this piece. Right, go on to the next. Right, x plus 1 times what would get me up here? Well, I would just need a 2. X plus 1 times negative 2 gets me negative 2 x plus 1. So you can have whole expressions that are shared amongst all the terms in your much larger polynomial or much larger expression, in which case we can factor out those binomials or polynomials they have in common. Right? It's a little weird, a little funky, but Right? We might get used to it more in section 6.2. All right, that should cover all the question types in 6.1 and removing a greatest common factor.